Hello everyone, this is Gerry Flores. I'm a photovoltaic engineer working with New South Wales farmers to help farmers and agri-businesses across the state by providing information about energy efficiency and renewable energy technologies. This is our webinar on solar technologies for agri-businesses. I'm just repeating this for the benefit of those who just arrived. This is one of several webinars that we will be providing as part of the New South Wales Farmers Energy Innovation Program, which is being delivered with the help and funding from the federal government's Energy Efficiency Information Grants Program. Oof, a mouthful. EEIG, it's called. If anyone has any questions, please don't yell at your screen or yell at your microphone or give us a call yet. Just pop your question in this chat box at the bottom of your GoToWebinar program. We will be moderating the questions and try to answer as many as possible during the question time of the webinar. If we can't get to your question then, we will also try to address your question via email, as we will have your contact details that you provided to sign up. So we'll try to answer your question with specificity that way. All right, now without further ado, we'll get going with this presentation. So welcome everyone. And let's just start by addressing, well, basically, how do we get here? Why is there merit to an energy innovation program and the rollout of efficiency measures at all? And the simple answer is that for most businesses, the green credentials are no longer the principal reason to install renewable energy or more efficient equipment. There's been recent price hikes for electricity and gas, combined with drops in the cost of renewable energy generators such as PV, which have brought the issue to the table on a purely financial basis. So this is the cost of electricity as given to us by ABS CPI data over the last 14 years. And as we can see, we've gone from about 10 cents per kilowatt hour in the 2000s to a weighted average cost across capital cities of 25 cents per kilowatt hour or more. Now, though gas markets aren't as transparent as the electricity markets, so apologies for the small number of data points on this graph, but we can see as well that gas prices have also skyrocketed in price. The wellhead price of gas has gone from about $3 per gigajoule to about $12 per gigajoule, and that means that people buying gas at retail prices are now experiencing costs that have gone up from about $10 per gigajoule to around $30 per gigajoule, or $30 cents per megajoule if you're more comfortable with that measure. However, as these other graphs show, we have the price of solar PV systems and solar modules has collapsed to very affordable levels. The top two graphs show on the left we have the residential PV price combined and weighted for all system sizes across the entire nation. And on the right we have a similar graph only showing commercial systems, however. And that doesn't go as far back, it only goes to May 2014. Both of these graphs at the top are provided by an aggregator of quotes called Solar Choice, which looks at this price index every month. And we also have the Australian Photovoltaic Institute. They did a national survey report of PV power applications in 2013, and that provided us with the graph that we have here at the bottom, which shows us that the price of solar modules has gone from about $9 per watt to less than $1 per watt. Now, that's just the solar modules. There's also been price reductions in inverters and installation costs and the entire balance of systems to a PV system. And that's basically why we're now addressing what to do with electricity prices with renewable energy from a financial perspective, not just because of the green credentials. As farmers have actually been at the forefront of the uptake of solar PV. The REX Agents Association conducted a study and generated a report where they showed that solar uptake has been substantial in rural and regional areas. Basically, average solar penetration in Australia is only 22%, but in rural and regional areas the average is way higher at 29%. And we can see this in this graph where major urban regions have an uptick of about 23 or 18%. So that's solar penetration of both solar hot water and solar PV systems, whereas rural and regional with high urbanization and regional with lower urbanization have much higher solar PV uptake of 31, 28, and 27%. So that means that even though rural and regional dwellings only make up 32% of all dwellings, they make up 42% of the number of PV systems installed across Australia. And more so, this isn't just a rich grab by cash grab by rich people, basically. The uptick of solar is represented almost equally across all income levels, with only a weak correlation which indicates that dwellings with lower incomes are actually slightly more likely to invest in solar. So across this axis we have our income level, and we can see that there's this slight trend line where if you're on a lower income level, you're slightly, ever so slightly more likely to invest in a solar PV system. Now, this may be an indication that solar PV and renewable systems are being used as a cost management technology, given that it provides them some cost relief from rising electricity prices. And obviously, we also see that rural regions, which are the red dots, each dot represents a postcode in Australia, have way higher proportion of solar on their residents and dwellings than major urban and capital cities, which are in green. So before we jump in and start talking a bit more about solar systems and solar hot water, I just want to remind everyone that clean energy is but one of the ways to manage rising energy costs. There are other pivotal steps that you should be investigating and actioning before moving on to a renewable energy system. And these steps are illustrated in what we call the energy management pyramid, which is the following. So the first step is to conduct an energy audit to establish your baseline, and that's the energy analysis, and it's pivotal, and that's why it's at the base of the pyramid. It's something that's very important and that will let you move on to the rest. The second step is to basically go after all the low-hanging fruit, so energy conservation and time of use management. If there's some equipment which is on which doesn't have to be on, turn it off, and if there's equipment that is being used at peak hour or at peak times of electricity, when electricity is more expensive, and it can be used at other times, then think about how to implement those strategies. After that low-hanging fruit has been addressed, then we move on to investments, possibly, in energy efficiency. So identify and invest in energy efficiency opportunities, such as retrofitting equipment. This could be, for example, as simple as swapping out your lights, so T8s to T5s or LEDs, halogens to LEDs, or if you have really old incandescents, swapping those out for CFLs or the like, or bigger investments, more strategic things, such as swapping out a pump with a more efficient pump, or swapping out a piece of equipment, be it a tractor, whatever is using energy, for a newer version that will likely be using less of it. Obviously, this goes with financial case analysis hand in hand to make sure that it's a sensible investment, because at the end of it all, we're going towards energy management and from a financial management perspective. So we have to make sure these investments will pay themselves off. After all that has been addressed, you will now be starting off with a new energy baseline, a new amount of energy that you're using, and that's what you should base off your renewable energy system off. That's what you should consider to meet with renewable energy. So renewable energy is the very last step in the energy management pyramid. So while it can be a lot easier and cheaper to just buy a solar PV system, there's a lot more rewarding going through this process step by step and then getting a system, a solar PV system that doesn't have to be as big because you're not using as much energy to begin with. But nonetheless, let's jump ahead and talk about some of the actual solar systems available for farms. So there's integrated PV systems, and what I mean by integrated is that they can be used to supply power to multiple types of equipment. So they're not a single-purpose generator. They're not generating energy for a single purpose, and that encompasses grid-connected PV systems, which are connected to the grid and can both generate and export. They can generate energy to be used on site or export energy, which can be rewarded. Less so to an extent now, but still. Or standalone PV systems, which can be for an entire residence, an entire business or even an entire block of land, basically. Single-purpose PV installations or single-purpose solar installations include, for example, water pumping for stock and domestic irrigation, and I'll go through those in more detail later, and of course solar hot water, which is a key opportunity for example, dairy farms, which have a need for high temperature water to conduct their cleans after the milking process. All right, now for the benefit of anyone who is new to the technology, I'm just going to give a brief and simplified explanation of solar cells. Solar PV refers to photovoltaics. PV, that's what it stands for. And solar cell technologies are those that convert sunlight directly into electricity, solar PV technologies, sorry. Now this is achieved by allowing incident photons, so that's photons in sunlight that are hitting the solar cell and are absorbed by a semiconductor material. Their energy is absorbed when they knock electrons in the semiconductor material loose from their atoms, and then these electrons are collected, let's say, due to the composition of solar cells, and are only allowed to flow in a single direction. The flow of these electrons therefore generates a direct current. Generally, multiple solar cells are stringed together in series in an individual solar panel, and then multiple solar panels are then connected together in an array to generate a usable amount of direct current electricity. The direct current electricity generated by these panels can then be fed to an inverter, which can convert this electricity into alternating current at the appropriate voltages that are required, so that it can be used by most appliances and equipment at home or in your business. Alternatively, you can keep the electricity as in its DC form, and there's equipment that can make use of DC electricity, and that can also be more efficient. So for the case of solar PV pumping, the case is usually better to have a DC pump, because there will be less efficiency losses from converting DC to AC and then having a pump. It's a lot more efficient if you just stay with DC electricity and have a DC pump in some cases. There's a slew of and types of solar. There's all sorts of solar panels and solar cells, but there's two main types of technologies that really dominate the market, and both of those are crystalline silicon. And the technologies are monocrystalline and multicrystalline, and they dominate the market by far. I think they make up something around 90% of all installations make use of these two technologies, and that's where we've seen a lot of cost reductions and a lot of development still. So monocrystalline are a bit more efficient, but they can also be a bit more expensive, and multicrystalline are less expensive, and due to recent technological developments, they're almost as efficient as monocrystalline. So the only reason someone should choose one technology over the other on the basis of efficiency is if there is a restriction on the amount of space available to install an array. So if you have a roof and you only have 6 square meters available to put a certain size system, and say multicrystalline solar panels are too big to fit in that system, then it might be good to address monocrystalline, which have higher efficiency. But in all other cases, efficiency, unless there's a space restriction, is essentially a moot issue. It doesn't really affect our design of solar systems. We tend to go with what's reliable and reputable, more so than just the efficiency of it. There's a few other technologies which I don't think we will see as much in in installations these days, but nonetheless they exist and they're getting better. We have mainstream, double quotes, mainstream thin film technologies such as amorphous silicon, which is also very reliable and a sturdy technology, just like monocrystalline and multicrystalline silicon. But they're less efficient, and they're less efficient by about half, so their efficiencies are up from 8 to 10%. But they can also be a lot cheaper. And we have cadmium telluride panels, which are also less efficient but a lot cheaper, but they're really only for the utility side of things. And there's reasons for that, which I will gladly take offline, but cadmium telluride panels will tend to stay as a utility technology only. And there's a few emerging technologies, so we have copper indium gallium diselenide, and we have organic solar cells, so plastic solar cells, which are flexible and perovskite cells, and a few other technologies which are yet to reach a commercial tipping point, let's say. But nonetheless, again, they're getting better, and we might see some panels which have these solar cells in the future. But I don't think they're very mainstream as of yet. Okay. So now let's talk about our resource, obviously, which is solar radiation or irradiance. As you know, the level of solar irradiance changes throughout the day and year. Mornings and afternoons have lower levels, obviously. Summer has more of them, and winter has less. A few terms to go through, so nomenclature. We have kilowatts, which are a unit of power, and kilowatt hours, which are a unit of energy. Now, we can make the analogy of energy and electricity being, in a way, very similar to water. So when we think of kilowatts or power, we can think about the flow rate of a tap, of water flowing through a tap. And when we think of kilowatt hours, we can think about how much water is in a container. And that's the analogy. Power is the flow rate in the tap, and then energy is the amount of water that you have. So conveniently, a kilowatt hour is the exact amount of energy which is generated or which equates to 1 kilowatt over an entire hour. So if you're generating 1 kilowatt for an entire hour, you will have generated 1 kilowatt hour of energy. Solar radiation is also measured in these units. So we have incident sunlight, which generates an amount of power over an area. So we measure it in kilowatts per meter squared. And solar radiation energy is measured in kilowatt hours per meter squared. So how much energy is received over a given time over that area will give us the kilowatt hours per meter squared. Conveniently, we also call 1 kilowatt hour per meter squared as 1 peak sunshine hour. And that's just a reference to help us size systems or know how much solar resource we have. Sometimes it's best to refer to them in terms of how many peak sunshine hours on average we have per day. And as I mentioned, grid-connected systems and solar PV in general has seen immense uptake in Australia. The most common type of system consists of solar panels connected to an inverter, which is changing DC into AC power, supplying energy to the residents and business, and if there's more energy generated from the system that can be used at any point in time, the energy is automatically exported to the grid so that other consumers in the grid can make use of it. Businesses who install these systems are usually rewarded for any exported electricity with what's called feed-in tariffs, and these are, the level of rewards are of varying levels. Obviously there's the solar bonus scheme, which is a 60-cent gross feed-in tariff, and there's now the new tariffs, which are at a recommended rate of only the wholesale price of electricity. But I'll get to those later. Importantly, there's now over 3 gigawatts of solar PV systems installed across Australia on rooftops, and this equates to basically 2 Hazelwoods. So the Hazelwood coal-fired power plant generates about 1.5 gigawatts. So over the last 12 years or so, but mostly in the last 3 years, we've installed the equivalent of 2 Hazelwood coal-fired generators in terms of solar PV across rooftops in Australia. The amount of electricity generated from PV has continued to grow and has sustained an average year-on-year increase of 56.4% per year over the last 10 years. And in 2013, solar PV generated around 1.5% of Australia's electricity supply, as we can see here. 1 of every 4 houses in South Australia has a solar PV or solar hot water system, while 1 of every 5 houses across Australia-wide has one as well. Okay, so grid-connected systems, who are they best for? Who are they tailored for? Well, they're a key energy-saving opportunity for people who are using power throughout the entire year and during daylight hours. And this means that they're key for intensive animal farms and other intensive producers such as horticulturists, hydroponics farms, and businesses with equipment running year-round, cool rooms, grain mills, frequent irrigation. The photo we have here on the right, for example, is for a poultry grower in the Lismore area who's put a 99 kilowatt system to supply the power required for his ventilation systems and equipment on his farm, while the photo we have there at the bottom is for a vineyard in the Orange region, which again has seen the benefit of installing one of these systems from, well, basically humongous savings in electricity costs. Now there's a few design factors, and it's good to start off with looking at our solar resource. So over a year, the average solar radiation available will vary for sites with different latitudes and different climates. Thankfully, however, solar radiation is somewhat relatively stable. Well, not stable, but it's one of those things that it's safe to say that every region in Australia will have a good solar resource, given the average solar resource of Australia. Nonetheless, you can use the Clean Energy Regulator's postcode zones for solar panels list to determine the typical electricity that you will generate at your location. Now, most postcodes in New South Wales fall under the Zone 3, which is this one. So if you have a 1 kilowatt system, you're expected to generate around 1,400 kilowatt hours per year, a bit less here. You must also remember that output varies from season to season. Summer and winter solar radiation in New South Wales often varies by 50% or more, depending on the location. And if you want more detailed solar resource information, you can obtain that through the Bureau of Meteorology or from proprietary sources such as the Australian Solar Radiation Data Handbook. Now, there's a link here to go get these postcode zones and the specific average generation per day. These links will be provided in a future email that's what we deliver to you after the conclusion of this webinar, because I do know that that's a big URL to just jot down, so don't worry too much about it. And this might also be provided as a PDF in the future, so don't worry too much about just jotting down these URLs just yet. You'll have a chance to get them off a PDF later. Other design factors obviously are orientation and tilt. Fairly simple. Orientation, you'll get the most energy from the system if you orient it north, facing north, and tilt, you'll get the most energy out of the system if you tilt it at a pitch equal to the latitude of the location. However, obviously there's cases where, given there's not as much reward from exporting power, we want to match our consumption with our generation as much as possible. So there's some cases where, for example, if you're using a lot of energy in the morning, you might want to orient your system towards the east, and that might be the case. For example, we've seen feedlots in certain places around in farms that have a grain mill that's running very early in the morning because they have to have that feed ready for the cows fairly soon. So they start up their mills at 5 a.m. or 6 a.m. and obviously there's not as much solar resource in the wee hours of the day. So orienting a system eastwards in that case might match the generation of the solar PV system a bit better with demand. And in the case of, say, a residence or accommodation, usually after people get back from work, they turn on the TV, they turn on the air conditioning, they turn on a kettle, they have and they use a lot of appliances. So in those cases, it might also be good to face the system westwards so that demand is met with higher PV generation as well. Now again, this is on a case, everything has to be looked at on a case-by-case basis, and we'd recommend for you to talk to your installer before making the decision. Tilt, again, similar conundrum. While we can generate more energy by just leaving it at the pitch equal to the latitude, if we make it a steeper pitch, we will get better generation during winter days, and if we make it a bit flatter, we'll get better solar generation during the summer days. So if your particular farm or business has some seasonal variations where you need more energy during winter, then it may be better to pitch it at a steeper angle, whereas the other case being if you need more energy during summer, there may be the case for having a flatter pitch. Again, case by case, has to be assessed. And mounting, so cheapest option is still to just have a fixed tilt and hopefully on a roof, because the mounting systems for roofs are a lot cheaper than a new ground-based mount. And there is also the option of having a tracker. Now this can be a single axis, so just changing the tilt of a system, or it can be a dual axis which both adjusts the tilt and the orientation of a system. So these can increase the generated power by 10 to 25%. However, they tend to be a lot more expensive, and you have to remember that you're going to be carrying out maintenance for this system because it now has a lot of moving parts. So the 10 to 25% benefit from increased generation is typically outweighed by the maintenance requirements and costs. So my suggestion would be to look at increasing the size of the array if you need more power before thinking about having any tracking modules or any sort of tracker. And we have here a graph provided by GSES that shows us how, with the tracking system, in this case this is a dual axis, we get more energy from the system during any given day. And interestingly enough, we also see we have this hump here at the start of the day, and that's because solar panels and solar cells also have a power relation to the temperature. And with increased temperatures, their power output decreases ever so slightly, which means at the start of the day, you get a bit more power out of them because it's still cool, whereas at the end of the day, even though they're getting energy from the exact same angle, the solar panels will be hotter and thus slightly less efficient. And then one of the most important things is sizing. Feed-in tariffs, as I said, have now been scaled back significantly in most states, and as a consequence, it is financially prudent to size your system so that it offsets a considerable portion of your electricity, but not so that it generates too much excess power which will be exported. Each generated kilowatt hour used on site represents a saving in the order of around 25 cents, and each exported kilowatt hour of electricity is only rewarded by 3 to 6 cents, and at least that's the case for new systems installed in New South Wales. A system which is too large will be more expensive and take much longer to pay itself back. And this is basically shown here. So we have a 3 kilowatt system and a hypothetical energy profile use of a dwelling. And we see the solar generation is this silhouette here, where the yellow part represents how much is being used and the red part represents how much is being exported. So in this case, we're using most of the power. We're saving a bit per day, $3.50, and we have a very good simple payback rate of 3.7 years. If we move on to a bigger system with the same profile, yes, we're making more savings per day, but this is pushing out our simple payback to 4.6 years. So over the lifetime of this system, it will generate a lot more savings for you, but you just have to consider what is your main driver here. Do you want a simple payback that's within 4 years or 5 years, or are you willing to go to a payback rate that's maybe more prolonged but will give you greater savings in the long term? A rule of thumb which I would recommend for your system is to use around 80% of its generated power. So size your system so that it's using about 80% of the power that it can generate. Because clearly we see if we go with a system that's way too big, then our simple payback will jump to 6 years, and this can be compounded even further on weekends when you're not using a lot of power. So it's good to make sure you get a system size that's appropriate. Talk to your installer, and remember, rule of thumb is you want to use around 80% of your power for your own consumption, so this value here. So moving on to pricing. As I mentioned, the price of solar PV systems and solar PV modules have gone down significantly in the last 5 years or so. They usually have a payback rate of anywhere from 3 to 6 years, sometimes a bit more if the system is a bit more complex, has ground mounting arrays or a few other bells and whistles, and might become a bit more expensive. But the internal rate of return is about 20% or more. These pricing trends can be accessed online, and we have them here. As if you click this, it'll take you to a search that shows you other months. So I'll show you that as an example, just quickly. So we have let's go with November, residential solar PV price index for November. Sorry, let's go with commercial. Okay, so we'll scroll down, and they've done all the survey and aggregation of quotes to give us some values of how much different size systems will cost. And of course, these are for capital cities. They haven't done a full regional study, but we can make some inferences and extrapolate. And obviously, we expect regional areas to have somewhat higher prices of these systems, mostly because there's a bit of a lack of competition, and also because of the issue of distance and having to transport these materials and installers out to the bush. So, for example, here we have a 10 kilowatt system. The average price in the city of New South Wales was about $13,791. So that means on $1 per watt, that's about $1.37 per watt for this system. So if you were trying to compare quotes from different installers, on top of making sure that you get more than one quote, getting different quotes, several quotes from various installers, refer back to the prices available here and see whether you're getting something that's above or below average in terms of the solar index PV price, the PV index price. If it's substantially above what the average is, then just talk to the installer who provided the quote and make sure that he explains why that is so that you're comfortable with it and you can move ahead with it if you desire. So I'll move on now to standalone systems. I know there's a lot to talk about with grid-connected systems, but there's a lot to cover, so sorry if I glance over a lot of stuff. As I said, if you have any questions, be sure to put your questions in the sorry guys, if you have any questions, be sure to type them in the chat box available here. We will try to answer as many as possible in the question portion of our webinar. And if we can't get to your question, then we'll try to get back to you with more specificity via email. When you registered, you gave us some contact details, likely including an email. And if you have a question that you want answered, feel free to send that question either via email or placing it here in the message box. And then we'll try to meet as many as we can. Okay, so standalone system. What we mean by a standalone system is a system that is not connected to the electricity grid. These systems can comprise energy storage to make use of collected solar energy during times of little or no sunlight. So for example, nighttime or cloudy days. Or they can also use, an energy storage can be, for example, a water tank. You're storing the energy, the solar energy collected by that solar PV system as potential energy in the water in the tank. This obviously permits the availability of power on cloudy days, and the key thing you have to compare it against is, well, if you were to get a connection point to the grid, which would provide you more flexibility, less maintenance, and maybe the possibility of then adding solar, how much does that cost? So the financial feasibility has to be compared with either a connection point to the grid, or for example, running a purely diesel-petrol generator. Sorry, a diesel or petrol generator. The most prudent system that we've seen financially is typically a system that generates solar energy, stores a daily or enough energy in a solar battery bank to last for a couple of days, and then for times when additional energy will be required, a diesel generator can be made as part of the can be added as part of the system, so that it can help to supply power when there is not enough being generated by the solar array, or when you want to top up some batteries. In this case, we have a system here shown for purely single-purpose water pumping, and I'll get into that a bit more later. Standalone systems, not too complex. There are key energy management opportunities for obviously isolated homesteads who have to maybe buy a couple of poles and some transformers and a connection point from the utility in order to get a connection point. Shearing sheds, which again have the same scenario. If they're very isolated and away from any connection points, it may be suitable to put a solar PV system combined with some battery storage or a diesel generator. And watering points with no grid connection, which I'll get to fairly shortly. So, watering points with no grid connection, that is solar water pumping for stock and domestic purposes. So an example of standalone system is these systems. And these have great potential for stock and domestic water pumping. When designed properly, they can give you a steady and reliable water supply. And we have here a picture of one that's been installed in southern New South Wales doing such a thing. Now, even though I've said that trackers are usually not required and having an increased sized array is usually better, these systems can also be sold modularly with a whole tracker and everything, and so these systems can be a bit more expensive, but they tend to be sold more as a module than put together piece by piece. Again, it includes, a typical solar system includes, as always, a solar array, system controllers, which are in addition to a normal grid-connected inverter, which just has an inverter. System controllers control, obviously, the power going down to the pump, and tracks the maximum power point of a solar panel. An electric motor to power the pump, and then the pump itself, which can be submersible or a surface pump. Here we have two exemplary diagrams showing a system with a surface pump on one and a submersible pump on the other, and one is pumping to a trough for watering for stock water, and the other one is doing a combined two-stage system where it first goes into a storage tank and then into troughs to provide for stock. Now there's multiple benefits, obviously, from stock and domestic solar PV pumping. Number one is obviously cutting bills for mains electricity and diesel. If it was a grid-connected system, then the electricity used for it can be offset. And if it was a diesel system to begin with, then you can usually eliminate a diesel system completely. There's also, operation is independent and more reliable, so it can be great for isolated locations, and helps to reduce the number of fuel reruns that you have to do. Removes the requirement for connecting to power lines and poles, removes noise, fumes, and fueling runs, as I mentioned. It's easily scalable. If you want more water, or more water is required, then the system can be made larger. And it's flexible. So it can also just be, in the end, just a grid-connected PV system with electric pump. Farmers that we've talked to have talked about fewer breakdowns and less maintenance, and have said that that's one of the key reasons that they love their systems, is that they don't have to go up there all the time and swap out the petrol or the diesel, and they don't have to fix as much stuff that just keeps breaking down. And obviously, protection from rising energy costs. So you're getting energy from the sun, which is sunlight, which is free, effectively. Designing these systems is a bit tricky, a bit involved. Main steps are to determine your daily and seasonal water requirements and the flexibility to those requirements. If you're using them for stock and domestic purposes, then there's probably a critical level of water supply that you absolutely need, and it's about building a system or designing a system that will absolutely be able to meet that requirement. In the cases of other types of systems, you can have backups, so you can have a backup generator that will help pump water if it's required. And the key steps to designing these systems are as we have here. So site assessment, tilt and orientation, calculate flow, then head, and then go on and select a pump and array. Now, we don't expect farmers to fully go out there and do all this by themselves. We are putting together some information to help them with this opportunity. But it's key to talk to your installer, or key to talk to your experts on irrigation and get their knowledge on what they think the requirements are and how best to address the design of the system. We will be delivering a new solar pumping guide called the appropriately Solar PV Pumping Guide. It's been developed in conjunction with OEH. New South Wales Farmers has sourced the help of various stakeholders and energy experts, including people from GSES, and produced this guide, which will be available very soon and will be presented in a future webinar. So that webinar will cater specifically to this opportunity, and we'll talk about only solar PV pumping. I can say, however, that if you're already on a roll and are soon to make an investment, there's a bit of help can be you can get a bit of information from some software provided by Novo Mono, such as solarcast.com. Here's a screenshot of that, and I'll provide these URLs later. Right, so a few people messaged me before the start of the webinar on using solar PV for irrigation. Now, we've made some, we've done a survey of farmers that are looking into this opportunity, and we've looked at the major suppliers that are looking to install systems for that, and it's definitely a viable opportunity for people that have year-round irrigation requirements, and that has been horticulture, such as orchards or vineyards and people using hydroponics as well, and drip irrigation, but it can get a bit more complicated when you have broadacre farming or crops which require large amounts of water in isolated events. So we have a blueberry farm on the top right of the water requirements for a blueberry plant, which are, we could say, somewhat stable through the year, and more so they match the availability of solar energy through the year very closely. So during the months of September through Feb, when the summertime, when there's more irradiance, we have a greater requirement for water, so the solar PV system will be able to work harder and get that water. And during the months of May, June, and July, the blueberries will not require as much water, and it's exactly the time when the solar PV system won't be able to provide it anyway. So for certain crops, it's a perfect match, and it can work very well, especially when that water is required daily. However, for example, we have here a cotton crop, which requires substantial amounts of irrigation in very isolated events during the year, which means that a big system has to be put in place to supply the water when it's needed, but it won't be paying itself back by being used throughout the whole year. So we commissioned Global Sustainable Energy Solutions, GSES, to help us make a hypothetical case and scenario of what it would take to have a system that's large enough to provide the pumping requirements of a large broadacre farm. And we provided information on the farm. This was a mixed farm that required around 60 megaliters of water per year, and this is their assessment of what would be needed in terms of an investment and what the financial case for it is. Sorry, the annual water requirements is not 60 megaliters, it's 170, and this is to meet several crops, and amongst them cotton. So we have what the farmer is currently using, which is a diesel water pump. So it's a diesel engine powering a pump directly, which has a very low capital cost, but high maintenance and ongoing fuel costs requirements. And that is expressed here, but you can see that even at the end of the assessment, once we tally up all the costs and reach the end of life of both systems, so this is a 20-year study, the solar water pump, the solar PV pumping system is still slightly more expensive than the diesel water system, but the threshold is very close. So we're fully expecting to see this becoming more viable as the price of a lot of the components drop, because the particular system that was used to make this assessment had this cost breakdown. So they had batteries and solar modules taking up the largest portion of the pie. Now solar modules have experienced a significant drop in price, and we still expect them to get cheaper, but not substantially. So this component might not be getting that much cheaper very soon. However, batteries, we've seen enormous developments in the chemistry and types of batteries, so this component could still shrink quite a bit. Obviously, inverters and the rest, installation, a lot of gains can be made there. So we fully expect a big system, solar PV system, to be viable for large broadacre irrigation farms in the future, because the threshold, as I mentioned, going back, is fairly close now. Okay, so solar hot water. As many of you might know, it's a widely deployed technology in Australian farms. It makes use of a solar collector made of materials that absorb heat from the sun very efficiently. Cold water travels through the collector, it's heated, and then returned to the tank. Hot water floats to the top of the tank, and colder water is taken from the bottom and returned to the solar collector. To assist with the circulation, some systems incorporate a small pump that is activated when the temperature difference between the water in the collectors and in the tank reaches a threshold. And when you use hot water, it is taken from the top of the tank where the water is the hottest. Now, usually these systems provide sufficient heating to provide all of the hot water needs on warm or sunny days, but they may fall short on cooler or overcast days. For this reason, the solar technology often works in conjunction with an electric or natural gas booster, which provides additional heat in order to reach and maintain desired temperature points for stored water. Now, there's two main types of technologies in solar hot water. We have flat plate systems and evacuated tubes. Now, it used to be a case where evacuated tubes were prohibitively expensive, extremely expensive, which meant that most of the installations being done were flat plate systems. But the benefits of evacuated tubes have shown their merits, and more so the cost of them has reduced substantially. So as you can see by this comparison, in most cases, evacuated tubes are now one of the most viable solutions for farms, and especially in dairies, which require high temperature water for cleaning after milking. Evacuated tubes are really the only technology that can achieve anything that's close to the high temperatures that are required. They're also a bit lighter. They don't. They can be easily replaced in that if a single tube breaks, then that tube can be replaced individually as opposed to the whole system. They can be a bit more expensive, but the difference isn't as bad as it used to be. So they tend to have lower payback rates of something similar to PV of around 4 to 6 years. Designing them obviously involves, well, identifying the space. You want north-facing roof space, again, similar to solar PV panels. The ideal position to maximize solar radiation is an unshaded north-facing roof. If there's not sufficient unshaded roof space, then you can still go with ground mounting. So just like solar PV systems, there can be ground-mounted solar hot water designs. Consult with your professionals. Solar thermal systems are often sized with ratings to provide a certain amount of hot water per day, but equipment dealers and professionals should be able to advise you as to which system will best meet your existing needs if you have requirements that are not for domestic, say if it's for a farm or a dairy farm. If possible, try to tilt for winter. So unlike solar PV panels, solar hot water systems should be tilted at steeper angles. This is because savings can be maximized if the system works best during the times of the year when there is greater demand for hot water and when it's harder to heat water, and that happens during winter. Therefore, a steeper pitch on a solar hot water system will optimize its performance when the sun is lower in winter days, and tilting the system for winter will help ensure that the system will not overboost temperatures during summer. So overboosting can also be a problem. I mentioned pricing. It's very similar to solar PV in that the payback rates are about 4 to 6 years, and the case for them is a bit better for dairy farms or farms which are using a lot of hot water or water at very high temperatures. A question I've been asked a lot is whether PV or solar hot water is the better technology to heat water, be it for domestic purposes or otherwise. And obviously, what seems to be the obvious answer is that everyone will say, well, a solar hot water system is meant specifically to heat water, but there are some niche scenarios where a PV system might be cheaper. So the short answer is each case requires an individual assessment and a case-by-case assessment. The efficiency of solar hot water systems is around 40 to 60% in that it collects heat energy from the sun and it transfers it to heat energy in the water. 40 to 60% efficient, as stated by Apricus Australia. Now, solar PV system, solar cells, commercial solar cells are not more than 20% or 21% efficient if you get a really good, expensive kind. So and then you would have to combine that with a resistive heater to heat the water in a tank. So at most you're going to be 20% efficient. So a solar PV system to supply the same amount of hot water as a solar hot water system would have to be larger. That's something that this gives us. So the likely answer is that for most farms undergoing a full upgrade, a solar hot water system is the better option, and it's best to upgrade a whole system, as including the storage tank, as this minimizes installation costs, and you can ensure that you have all components are warranted and expected to last a deemed amount from the get-go as you organize that with your installer. Nonetheless, there may be cases where PV may be cheaper. For example, if you already have a solar PV system and if you already have a storage tank with an electric heater and you're thinking about putting solar PV anyway, then it may be better to just oversize the solar PV system so that it can also cater for your solar hot water requirements. Now, this option, the savings from it, can be further maximized by installing devices that automatically turn your solar hot water system on when there is too much excess solar generation. One of these is, I don't have the name with me at the moment, but I'm happy to follow that up via email later. So let's talk about the due diligence on installers and how to find the good ones. Well, it's not an easy thing. There's a lot of installers out there. There's probably thousands now in the whole of Australia. So it's good to select one that meets a few criteria. So number one, make sure that the panels that you get have a warranty. Now the industry standard warranty is 80% of nominal power after 20 years. And if that's not offered, or at least that isn't offered, then that's probably not a panel you want to be buying. The inverter is typically the first thing to fail in a solar PV system. So the warranty, make sure that the warranty for the inverter is strong and that there's a replacement schedule or some sort of contract to allow replacement of an inverter if there's any failures. The warranty on installation, there is not as industry standard. Well, the standard isn't as solid in the industry as it is for panels. We've seen installers with little installation warranty of only 2 years, and we've seen some with 5. We've seen some up to 10 years of warranty on the installation. The Clean Energy Council has a job of accrediting solar installers that meet certain criteria, so be sure that they're accredited by the Clean Energy Council. And if possible, try to get products that are Tier 1 or Tier 2. Now this is a bit ambiguous because, again, Tier 1, Tier 2, and Tier 3, the definition of these isn't industry standard either. However, Pike Research has identified these criteria for Tier 1, Tier 2, and Tier 3 for solar PV systems. So the best ones are effectively Tier 1, but they can come at a price premium, and it's not always financially wise financially easy to get a Tier 1 system, so it might not be the best option. Make sure, however, that you do get products which have a presence in Australia and that the installer is reputable and experienced. There's ways to get comparisons to get several quotes to compare. There's 2 sites which I use to sort of test the market for what's available. That's solarquotes.com.au and solarchoice.net.au. Again, I'll provide these in the future, but I'll just show you an example of how this works. So basically, you fill in well, this would start the whole process of finding the quotes. You fill in all your details, and after that you will get 3 quotes from 3 installers, and then you can compare those. And similar thing with Solar Choice, they have the request quote comparison process, which again you will supply them with the information if you already know sort of what system you're looking for, or you can just say I'm looking for a solar system, and they'll get back to you with 7 installers in your local area. And both of those services are free, so I would recommend before you select any installer that you make sure you make use of those systems and that you compare them against compare the quotes that you get. So now on to costs, incentives, and financing. So there's a few incentives in place that still benefit or reward the installation of renewable energy. We have the small technology certificates, which are also relate to the renewable energy target. So the renewable energy target has the target of achieving a certain amount of energy by 2020. At the moment, it's 41,000 gigawatt hours from renewable energy sources, and that is also, there's a component to that has to come from small generation units, or SGUs, which are typically the ones that farmers and businesses would install. And these are anything from 1 kilowatt or less to up to 100 kilowatts. Now, when you install a system under this program, STCs can be generated on the expectation of the amount of power and the amount of energy that will generate over their their life, or I think they have a deeming of 10 years or 20 years. And those certificates will usually be handed over to your installer so that he may trade them. And by doing that, the installer is able to provide you with a system that is cheaper. So usually the STCs are very transparent to someone who's installing a system. They never have to worry about them. But just be aware that your installer is offering you a better price because he is able to produce these small technology credits from the system which he installs and obtains some funding from it effectively. There's also ESCIs, which follow a similar model, but instead of being for the generation of renewable energy, they are for the savings of energy. So these are energy saving credits from the energy saving scheme in New South Wales, and that means that there's certain products which you can buy, such as lights or efficient pumps or efficient equipment, which generates ESCIs, and then it's in a similar way the installer or the seller of those lights will be able to offer those products at a cheaper price because he will be recouping some of his costs by selling the ESCIs that your project allows him to generate. There's a few financing options which are coming up as well for solar. Some of for smaller systems, some installers now allow interest-free financing where you'll be able to pay off a system over, I think, a year or two in small payments. And there's also the solar leasing model. Now, the solar leasing model involves basically installing a system at your residence or business, but not owning them. And then you will be contracted to buy your electricity from the installer, and then the installer will make money by obviously selling the electricity generated from your system and from the small margin between what you pay him for and what he's able to sell the electricity for. Now, that's good because the reason solar leasing works for a lot of people, and it's been the #1 financing option in the U.S., is because it means that most people can get a system with no down payments whatsoever. That can be an option, but it hasn't been a popular one in New South Wales or Australia. I'd also recommend, although I don't have a link to it here, but I will be providing it in some additional content that will be sent to you later, that you check out the financing options for renewable energy investments that has been put together by the Office of Environment and Heritage. So they've put together a report that goes into a lot of depth of what the options are for businesses looking to invest in or businesses looking to install large renewable energy generators and how they can obtain finance for them. And obviously, if you're a really large business, then you can go ask the Clean Energy Finance Corporation for a loan that's at a much lower rate than what your bank will offer you, as they're trying to incentivize the installation of the installation of renewable generators. Again, some questions I received before the webinar were about the costs and whether the economics of renewable energy and whether they hold up against other technologies. Now, this is from the case in Germany, where we've seen a humongous uptake of solar renewables as well. And this is called the levelized cost of electricity, or LCOE, which is basically our way of comparing different generation technologies on a pure cost basis. And these bar charts indicate the range at which different technologies can generate their electricity to add to the grid. And we can see that PV is still more expensive than certain technologies, although it can be cheaper only just than certain generation technologies such as combined cycle. And then the specific point in which they land here will depend on a variety of factors, such as proximity to connection points, solar resource, et cetera. And wind, of course, is one of the cheapest options to generate energy. If you're talking about a new build, So, and this is more the case, obviously, for large wind turbines, where they can be cheaper. Obviously, offshore, the price can be a lot higher. So these levelized costs of electricity, this is in euros, take into account a variety of factors such as the cost of capital, installation, decommissioning, and any revenue made or administration and revenue made from the actual sale of electricity, etc. So supposed to be encompassing all income and cost flows to make these numbers. Of course, this is the case for Germany. So in order to look at what we have in Australia, we can resort to the Bureau of Resources and Energy Economics, who have made their own assessment of the levelized cost of electricity, which includes, as I said, the carbon price, CO2 transport and sequestration cost, plant capital cost, owner's cost, fixed and variable cost, fuel cost, and economic escalation factors. Now, you might be wondering, wait a minute, carbon and CO2 transport and sequestration. After the repeal of the carbon tax, they have done this amended graph, which shows what the prices are with the carbon price set to 0. So even though it takes into account the carbon price, in this particular case, it's been set to 0. So the carbon price is nil. And we can see still that a solar and coal hybrid is one of the cheapest ways to generate energy. But solar PV is a wide bar, which means it can be very cheap at some points or it can be very expensive. And then we have all the other types of technology. We have our wind, like I mentioned, onshore, which can be cheap or it can be slightly more expensive, and of course supercritical black hole, which can be one of the cheapest ways to generate energy as well. So in terms of cost, it's renewables in many cases can be comparable to our mainstream ways of generating energy, as is shown in this report that was put together by the Bureau of Resources and Energy Economics. And I was also asked to comment on the current state of battery technologies and prices. Now, from the farmers which we've engaged with, we've noted that pricing is still prohibitive for a lot of scenarios. The price points for the capacity of batteries installed are around $750 to $1,000 per kilowatt hours of installed capacity. Now, that is still a bit too expensive, and if we amortize the capital costs and the maintenance and the time taken to set the system up over its lifetime, which in the case of batteries is usually 10 years, in some cases we arrive to an average cost of about 20 cents per kilowatt hour or a bit more. However, you have to take into account that requires maintenance, requires a lot of investment, and if you are currently on grid electricity, we're not quite there at the point of grid defection. I don't think that's really sensible by itself. However, it is starting to look like a viable option to install systems which are hybrid solar plus batteries, so that we can conduct peak shaving or shifting of power use from peak hours to non-peak hours, and then using our solar generation energy in our battery to make up the difference when needed. There's also various types of batteries and chemistries, and there hasn't been a clear winner yet, and that's made the selection of batteries and installers very difficult, because the controllers have to be set up for that particular chemistry and the particular voltages of a battery type. And with no clear winner in sight, it's hard to have an economy of scale for a particular battery if there's all different types of batteries and they all have similar levels of adoption, so no clear winner yet, except for lead acid, which still dominates, but obviously it has a lot of disadvantages in although it's cheaper, it's also a lot bulkier and requires substantial maintenance. And this is what I was talking about before. Obviously, the pivotal future role of batteries is to be able to cater for all that lost solar PV generation, which is just exported to the grid for about 3 to 5 cents of reward. If that can be captured and put in a battery, then it can help us shave peaks used by a business or a residence happen later into the day. So that's where we're moving towards. And this is something that's also going to be extremely pertinent given the conclusion of the New South Wales Solar Bonus Scheme. So the New South Wales Solar Bonus Scheme will end on December 31st. So there's quite a few systems out there that have been installed at the largest system size that was allowed for the program, for the scheme, which was 10 kilowatts. And it's a very generous and profitable reward program, which gave farmers who installed a system about 60 cents per kilowatt hour generated, regardless of whether it was used on site or it was exported. However, this will end on December, I forgot to add the year here. This will end on 2016, December 31st, not just December 31, 2016. I'll adjust that before sending the updated PDF, which means that when that happens, there's going to be a lot of solar PV systems, which are probably way too big for the amount of energy that's being used on their site. So they need to find something to do with all that energy, because it's not going to be rewarded by a tariff anymore. And that's where we think batteries might come in to hopefully give that system increased lifetime and utility. As to whether the timing of cheaper batteries will be met by that deadline, that's really up to speculation at this point, but it's obviously an exciting development that we're keeping an eye on. For more information, New South Wales Farmers has collected and produced a lot of information on energy efficiency and renewable energy. We have over 35 fact sheets on energy planning, energy purchasing, efficient farm vehicles, energy and irrigation, renewable energy, and energy in farm facilities such as sheds, poultry sheds, shearing sheds, all sorts of facilities on farm, which can be accessed by going to AgInnovators and the New South Wales Farmers website. So there's a URL there which you can access to get there. We also have our energy innovation planning tool, which allows anyone to basically conduct their own energy assessment. It's an Excel-based tool that allows people to input their electricity and energy use profile, and it will provide them with some suggested opportunities that they can do. We have our AgInnovators web portal, our Clean Energy Council, and the Australian Solar Council, which are and the Renewable Economy website, which are good resources to read up on the developments of renewable energy. And especially the Clean Energy Council might be a good resource to check on installers and the quality of an installer. New South Wales Farmers is soon to launch a solar PV pumping guide and a guide to on-farm energy generation. So the solar PV pumping guide is a substantial document of over 100 pages that goes into great depth on how to design and how to go about analyzing the opportunity of a solar PV pumping system. It will cater to both stock and domestic purposes as well as some of the continuous irrigation scenarios. So that'll be available fairly soon, as well as our guide to on-farm energy generation. So this will tackle all sorts of renewable energy generation, not just solar, but also obviously wind and waste-to-energy technologies, and that's soon to launch within the next month or so. So keep an eye out for these two reports, which will be provided soon, which I mentioned are these two. We will also be having a waste-to-energy webinar, which is taking place next Tuesday and delivered by energy expert Fernando Johnstone from Energetics. So click here to attend. I'll provide the URL to you guys after this webinar. So that brings us to questions. So I have a few questions here which Tracy has moderated for me and provided me. I cannot go through all of the ones that have been provided, so I'll try to do as many as I can. There's a few that have come in through emails recently, but I'll just try to tackle these that I have here. Okay, so one of the questions is, what is polycrystalline? So polycrystalline is is essentially another name for multicrystalline. So multicrystalline or polycrystalline silicon solar cells refer to solar cells that use silicon, but the silicon has been purified and then solidified in a mold as opposed to using what's called the Czochralski method. So if you use the Czochralski method, the ingot is drawn from a seed, and that generates very pure and very defectless silicon, and that's called a monocrystalline silicon wafer. Whereas polycrystalline or multicrystalline is when the silicon, which is highly purified, is taken to a mold and then effectively let to solidify in the mold. And that introduces a lot more, well, a few more defects and different crystal orientations, which is why when you look at a multicrystalline solar panels, you see these sort of shades of different blues, and those are all the different orientations of the crystalline. The silicon crystalline structure, effectively. So polycrystalline is effectively the same as multicrystalline. Our next question is, are there government subsidies available, and if so, how are they calculated? I understand there may be a subsidy called STC. So as I mentioned in our presentation, there is STCs, and those are different from the large generation technology credits. So we have, from the renewable energy target, there's two types of credits. There is STCs and LGCs. And STCs are really what caters for most farmers and businesses who are putting systems up to 100 kilowatts. These basically deem how much energy the way these are generated is an installer will obviously notify the clean energy regulator that they're installing a system and that the system is of a certain size, and then with a formula it's calculated how much energy is expected to generate over a deemed period. I believe this deemed period is 10 years. And this energy calculated is expressed in megawatt hours, and then for every megawatt hour that is generated over its lifetime, it's the system merits 1 STC. So I believe for a 1 kilowatt system, if we go back to our postcode zones, we'll be able to see the expected STCs that can be generated from it. So if we go here, we have a 1 kilowatt system will generate 4.44 kilowatt hours per day, which equates to, let me just see if I can get my maths here right. Sorry, I'll have to do the math for it later, but I believe per megawatt hour the payment from an STC is, I think at the moment, $30-something. So once you know how many megawatt hours your system will generate over 10 years, you can calculate how many STCs it will be able to generate. Okay, do the average prices you have shown for a system included installation? So this is another question asking if the prices I showed include installation. So the prices shown in these graphs, I'll just go through, do include installation. Not the one in the bottom, the ones at the top, these prices include installation, GST, and also the discounts available through the STCs. So that's really the final price per watt. In the case of commercial, I believe they may not include GST. Actually, I might have to double check on that. GST may not be taken into account on either of them, but they do include installation. They include all the equipment to have a solar system ready to go, effectively. These are for these two graphs, and those are also the prices shown by Solar Choice in the website. Those include installation as well as the components. Do the average prices shown include any rebates? Is the next question. Yes, so the STC component discount is taken into account in the prices shown here. But the Solar Choice also publishes the component of the prices, which is made up of a rebate. They don't publish it in graph form as you hear, but they do publish it as an average figure. And the average figure is that for every watt installed, there's about 60-something cents, 65 cents, let's say, of a discount through the STC rebates. So without the rebates, we'd expect prices to go, for example, in the case of today for a residential system, the weighted average price is 1.75. We might see that moving to 2.6. Sorry, the average is 1.8 or so, and that might move to 2.4. So without the discount, we would see a jump probably up here. So the discount is a substantial proportion, which equates to almost the entire fall that we've seen in the last 2 years. And in this case, commercial solar PV systems would be way more expensive without the rebate. Is there any reason to think that any government subsidies will be removed in the foreseeable future? Now this gets obviously a bit, dives a bit into politics. From what we've seen recently, it seems that the STC rebate scheme is fairly well protected. I cannot make I can't express anything more than speculation, but I believe the STCs are fairly well defended, which means while it's not certain, it's looking likely that that will remain at least for another couple of years, at least, well, possibly till 2020, but that's really speculation. I cannot be certain of that. When do I expect long-life batteries will be available for storage so that there is no need to draw from the grid at night? Yep, so when, again, is this going to happen? The answer for that is, again, very speculative. I can say that there's been humongous international developments into the manufacturing of new batteries, and more than that, the manufacturing of batteries at a large scale. So not making bigger batteries, but making a lot of them in really, really big plants. And the principle of economies of scale says that as you make more of something, the price per unit of such a thing will fall. So from a purely economic standpoint, we're expecting the price of batteries to come down. As to when this will reach thresholds which make it more viable to install, say, a hybrid system so that we can use solar energy at night, that is a very case-by-case question to be answered. I cannot really provide more than speculation again. My hope is that price points will reach a level that is good enough to make these systems viable by 2017, because the solar bonus scheme ends in 2016 on the 31st of December. But that is nothing but hope. One of the biggest international developments we've seen in the manufacturing of batteries is obviously Elon Musk and his company Tesla Motors, which is manufacturing, is currently building the largest lithium-ion manufacturing plant in the Nevada desert. It's called the Gigafactory, and you can look that up, and it's one of the biggest investments in future-looking, forward-looking, renewable helping technology such as batteries. So there's hope there again that will allow us to get to cheaper, not just cheaper cars. His drive to make this power plant is, sorry, this manufacturing plant is to have cheaper batteries for his car vehicles, his electric car vehicles. However, we think that with that increased production, we'll see those price points and those economies of scale benefit other industries that use batteries, such as the renewable energy industry. I have another question here. It says, what are the additional solar hot water requirements for hydronic floor heating in an average-sized house for off-the-grid heating on farm? Okay. So floor heating in an off-grid environment, that's a fairly that's a very interesting question. That'd be a great luxury. As far as the requirements into the quantity of water, I wouldn't be able to tell you how much water or how much heat is required for floor heating using solar hot water. I would be able to tell you that it's definitely doable, but I haven't seen in our as part of our EIG program, we haven't really seen that particular use case of solar hot water. So floor heating is something that we haven't really seen yet. I can't, again, that would, in order for me to look at that, I would have to take it offline and maybe respond to you via email. Another question I have, as a generalization, is it more efficient to have a PV solar pumping solution to transfer water than a grid-connected solar array that generates electricity to reduce your normal bill? I guess there's the solutions for in this case, if our main target is to try to reduce our energy bills, and the pumping of water is taking up a lot of that energy, or is making up a large portion of our energy bills, we first have to analyze, well, what's using the power? Is the system connected to the grid? If it's not, then is it diesel-based? If it's diesel-based, then we will assess that particular pump or that particular bore compared to a PV system, a standalone PV system, separately. And then we might assess, well, what is the case of bringing a connection point to that point look like? Because the benefit of bringing a connection point to a bore or a solar or a pump is that you can therefore add, well, you can after that add solar PV to the mix, and it no longer matters where the solar PV is located. As long as it's on a similar line, you will get the benefits of reduced energy bills, since you'll be helping offset not just what's, say, on your residence, but also what's on your solar bore. I'm sorry, on your bore. So that's, as a generalization, I would say, is it more efficient to have a PV solar pumping solution or a grid-connected solar array? I think the efficiency can be very comparable for both. I think if you put a PV system on your house and then have a normal electric motor running a pump, that's will achieve a similar efficiency to having a PV system right on the bore, drawing the water directly through DC electricity. It may be a bit more efficient, given that there's no conversion from DC to AC in the case of having the PV system right there on the bore. But then you have to consider that with other factors which may push it the other way to being less efficient, in that if it's an off-grid standalone system, there's less control over how much water gets pumped, and that can influence the efficiency of the system as well in some scenarios. Obviously, if you have a storage tank, then that can be taken care of. I think my answer to that would be that it's fairly equal. Another question we have is, what about the use of solar for a silo-based grain dryer? So that's one of the things that was actually taken out of this presentation, unfortunately, because it was covering a bit too much, was grain drying technologies for farms and using solar for those purposes. That is something that I haven't touched on this webinar, and I'm afraid I'll have to take offline. But you might be interested to know that we're putting together a fact sheet on that particular topic, and that will be available through AgInnovators and the New South Wales Farmers website fairly soon. So that covers all the questions I have time to address at the moment. If there's anything else, or you want a bit more specificity, I really did go through a lot with just a glance over. If you want a bit more information on any particular topic, remember that we have our solar, sorry, not our solar, we have our EEIG hotline, which is our, oh, I can't believe it's not there. Sorry, that's meant to be here, so I'll just leave our energy hotline, which is 02-9478-1013. So if you guys want more specific information for any type of on-farm renewables or energy efficiency, as part of the Energy Innovation Program, we're still available to progress some we'll progress this program and provide you with advice over the phone and via email. So that's the number. Otherwise, contact us on Gerry F at newsouthalesfarmers.org.au. And that concludes our webinar for today. So thank you everyone for joining. I hope I gave you a bit of information that was of use to you. If I didn't, like I said, just pop me an email or give me a call, and I'll be glad to be of help. Thank you very much.